October 14, 2024. NASA launches a $5 billion spacecraft toward Jupiter's moon, Europa. The mission? Find signs of alien life in Europa's subsurface ocean. The same week, companies submitted applications to mine the deep ocean floor. The goal? Extract trillions of dollars in rare metals from ecosystems we've barely explored. Here's the problem. The best place to learn how to find life on Europa is Earth's deep-sea hydrothermal vents. And we're about to bulldoze them. This isn't an environmental story. This is a story about a choice we're making right now, this year, that could determine whether we ever find life beyond Earth. Let me show you what I mean. In March 2025, Europa Clipper swung past Mars, building speed on its journey to Jupiter. It will arrive in 2030 and spend 4 years studying Europa, a moon covered in ice, hiding an ocean twice the volume of all Earth's oceans combined. Scientists believe Europa's ocean floor has something crucial: hydrothermal vents. Places where heat from the moon's core meets frigid ocean water, creating chemical reactions that could power life. Sound familiar? This is what NASA calls an Earth analogue, a place on our planet that resembles conditions on other worlds. If you want to know what life on Europa might look like, you study Earth's hydrothermal vents. To get our microbes, we use submarines, sometimes human-occupied, sometimes robotic, to dive a mile below the surface. Because Europa's conditions might be similar to these microbes' environment, we think Europan life, if it exists, should look something like our own hydrothermal microbes. In 2025, NASA awarded Holden's $621,000 to study these vents as Europa analogues. Not in the future, right now. These aren't just weird deep-sea creatures. They're our Rosetta Stone for alien life. Every discovery here teaches us what to look for up there. 1977. First hydrothermal vent discovered. Life without sunlight. 2001. Low-temperature vents found. Survive billions of years. 2023. Red Sea vents with iron-based metabolism. Completely new biochemistry. 2025. Arsenic-tolerant worms that biomineralize toxins into survival tools. And here's the kicker. We've explored less than 5% of Earth's deep ocean. We're discovering new vent systems every year, each one revealing biochemistries we didn't know were possible. And commercial mining operations, the kind being approved right now, could destroy these systems before we've studied even half of them. July 2025. The International Seabed Authority meets in Jamaica. On the agenda, finalizing regulations for commercial deep-sea mining. But there's chaos. 32 nations are calling for a pause. Others want mining to start as soon as possible. And then, in April 2025, a Canadian company called The Metals Company did something unprecedented. They announced they would bypass the international framework entirely and seek mining permits directly from the United States. The ISA Secretary General called it a violation of international law that would fundamentally violate the principles of multilateralism. Translation: the rules of the game just changed, and the clock is ticking. So before we talk about mining, or economics, or regulations, let's talk about what these places actually are. Because once you understand what we're looking at, the stakes become very, very clear. February 1977. Scientists in the submersible Alvin descend to the Galapagos Rift, expecting to find barren volcanic rock. They're here to study geology, not biology. What they find changes biology forever. Giant tube worms, 6 feet tall, clams the size of dinner plates, swarms of white crabs, an entire ecosystem in complete darkness, 2 miles below the surface, thriving without a single photon of sunlight. For 3.8 billion years, we thought all life on Earth depended on the sun. Photosynthesis. Plants capture sunlight. Animals eat plants. Circle of life. Wrong. These organisms run on chemistry. Chemosynthesis. They harvest energy from hydrogen sulfide and other minerals spewing from volcanic vents. No sunlight required. And here's where it gets profound. When scientists mapped the evolutionary tree of life, they found something stunning. The oldest organisms, the ones closest to the last universal common ancestor of all life on Earth, are thermophiles, heat lovers, vent dwellers. Life didn't begin in a warm, shallow pond. It began in darkness, in heat, in crushing pressure, in conditions we once thought were impossible. Now imagine you're designing a search for life on Europa. You need to know, what does life look like when it doesn't need sunlight? How does biochemistry work in eternal darkness? What biosignatures should your instruments detect? You study Earth's vents. They're the only example we have. August 2025. Scientists publish findings on Paralvanella hessleri, a worm that lives in the hottest part of hydrothermal vents in the West Pacific. It survives in water hot enough to melt lead. How? It accumulates arsenic, one of the deadliest poisons on Earth, in its skin cells. Then it reacts that arsenic with sulfide from the vent fluids to create orpiment, a stable yellow mineral. It turns poison into armor. The lead scientist, on his first deep-sea expedition, said he was stunned when he saw these bright yellow worms on the ROV monitor. They discovered a detoxification mechanism biology textbooks don't describe. Fighting poison with poison, they called it. Now, if life on Earth evolved this solution in this specific environment, what solutions might life on Europa have evolved? What else is possible that we haven't imagined yet? October 2025. Another discovery. The Hydrothermal vent fields in the Red Sea, the largest active low-temperature iron oxide vent system on Earth. Scientists reconstructed over 300 microbial genomes from these vents. Most had never been seen before. The dominant metabolisms? Iron-based. Not sulfur, not methane. Iron. Every vent system we study reveals a different solution, different chemistry, different energy sources, different forms of life we couldn't have predicted. We've found about 700 active vent fields worldwide. Scientists estimate there are between 50,000 and 100,000 total. We've studied less than 1.5%. Europa Clipper carries 9 sophisticated instruments designed to detect biosignatures, chemical and physical markers of life. But those instruments were programmed based on what we know from Earth's vents. They're looking for patterns we've already seen. What happens if we destroy the vents we haven't studied yet? What if the key to recognizing life on Europa exists in a vent system we mine before we discover it? That's not a hypothetical question, because mining is happening. And it's happening in the areas where these vents exist. The Clarion-Clipperton Zone, a region of the Pacific Ocean between Hawaii and Mexico, roughly the size of the United States. 4,000 meters down, the seafloor is carpeted with polymetallic nodules, potato-sized rocks packed with cobalt, nickel, copper, and rare earth elements. $16 trillion worth. Industry estimates say this one zone contains more copper, cobalt, nickel, and manganese than all known land deposits combined. And we need these minerals. The green energy transition depends on them. Electric vehicle batteries, wind turbines, solar panel systems, grid-scale energy storage. Without these metals, the transition to renewable energy becomes complicated. The mining process sounds simple. Lower a collector vehicle, essentially a combine harvester for the ocean floor, attached to a riser pipe. The collector sucks up nodules and pumps them to a surface vessel. Separate the minerals, discharge the waste. Simple. Except the collector is the size of a school bus and weighs 300 tons. And each collector creates a sediment plume that spreads for hundreds of kilometers. Recent studies show these plumes can persist for weeks, suffocating filter-feeding organisms, disrupting communication and navigation for marine life, and destroying fragile ecosystems that have existed for millennia. Here's a number that stopped me cold. To yield the equivalent amount of nickel currently mined on land, you'd need to mine up to 2,000 times more area at sea. And recovery time? Scientists studying areas where test mining occurred decades ago found essentially no recovery. The ecosystems don't bounce back. They're just gone. Which brings us back to the International Seabed Authority, the organization tasked with preventing exactly this kind of destruction. The ISA was supposed to have mining regulations ready by July 2023. They missed that deadline. Then they set a new target, July 2025. July 2025. The ISA Council meets. Do they finalize regulations? No, they're still negotiating. What threshold of environmental harm is acceptable? Who pays if things go wrong? How do we ensure benefit sharing with developing nations? Should we wait until we have better baseline environmental data? The metals company, one of the front-runners for the first commercial license, had been saying they'd prefer to wait for final regulations. Then, in April 2025, they announced a different plan. Skip the ISA entirely and apply for permits under US law. Here's the problem. The US isn't even a member of the ISA. It never ratified the UN Convention on the Law of the Sea. So when a US company starts mining international waters without ISA approval, what happens? Some legal experts warn this could trigger what one called a Wild West scenario, where countries start ignoring international agreements and mining wherever they want. China is watching. They've already interfered with deep-sea explorations in disputed waters. If the US goes rogue, what stops China from doing the same? The entire international framework could collapse. And that framework, however imperfect, is the only thing standing between managed exploitation and a free-for-all. But let's bring this back to astrobiology, because that's what makes this different from other environmental debates. The Clarion-Clipperton Zone doesn't just have nodules. It has active and inactive hydrothermal vent systems. The mining zones overlap with the very environments we need to study for Europa. The metals company's application covers 25,160 square kilometers for commercial mining, plus nearly 200,000 square kilometers for exploration. For comparison, the entire area humans have explored for hydrothermal vents globally across all oceans in all of history is roughly 1,200 square kilometers. We're about to industrialize an area 200 times larger than everything we've ever studied. It's like deciding to pave over 99% of a library before reading even 1% of the books. You might lose nothing important, or you might lose the book that contains the answer you desperately need. And we need that answer, because in 2030, Europa Clipper arrives, and humanity will be searching for life beyond Earth with instruments calibrated using incomplete data from a library we're currently burning.
Let's be fair to the other side. We genuinely need these minerals. By 2040, demand for cobalt is projected to increase by 460%, nickel by 300%, copper by 250%. The renewable energy revolution creates real, urgent demand, and land-based mining has its own horrific environmental impacts. Child labor in cobalt mines, toxic runoff poisoning communities, habitat destruction. If we're going to mine somewhere, maybe deep-sea mining is the lesser evil? Except, there are alternatives we're not fully exploring. Urban mining, extracting minerals from e-waste, already recovers significant amounts of copper, cobalt, and rare earths. A 2025 study found that aggressive recycling programs could meet 25 to 40% of projected demand through 2050. New battery chemistries using more abundant materials, sodium-ion, iron-air, are entering commercial production. They don't perform as well as lithium-ion yet, but they're improving rapidly. And then there's asteroid mining. Yes, it sounds like science fiction, but companies are already testing the technology. A single metallic asteroid could contain more platinum group metals than have ever been mined on Earth. Timeline? Asteroid mining is probably 15 to 20 years away from commercial viability. Deep-sea mining could start in the next 2 to 5 years. So the question becomes, can we wait 15 years to protect ecosystems that have existed for millions? Or do we need the minerals so badly that we're willing to sacrifice knowledge about alien life to get them a decade earlier?
John Barros, University of Washington, Oceanography. Hydrothermal vents represent the cradle of life, not just potentially, but actually. Every insight we gain about how life began and persists in these environments directly informs our ability to recognize life elsewhere. We can't afford to destroy the textbook while we're still learning to read. And here's what keeps astrobiologists up at night. We don't know what we don't know. Every new vent system reveals unexpected biochemistries. Europa Clipper will measure magnetic fields, analyze ice composition, detect organic molecules, map ocean thickness. But it can only recognize patterns we've already seen. It can only detect biosignatures we've already identified. What if Europa Clipper returns data that's ambiguous? Not clearly life, not clearly geology. Edge case stuff. How do we interpret it? We'd turn to Earth analogues. We'd study similar conditions in terrestrial vents. We'd look for comparable examples. Except those vents would be gone, mined, destroyed, irretrievable. It's the Library of Alexandria problem. We know burning the library lost humanity centuries of knowledge. We don't know exactly what knowledge, that's the point. You can't miss what you never knew existed. But the loss is real. Now, I want to be clear about something. This isn't anti-technology. This isn't anti-progress. This is about sequence.
Path 1. Mine now. Extract minerals. Destroy unstudied ecosystems. Hope we didn't lose anything crucial for astrobiology. Path 2. Study first. Map the vents. Catalog the biochemistries. Establish marine protected areas around critical sites. Then mine the areas that aren't scientifically essential, if we still need to. Path 1 gets us minerals in 2027. Path 2 gets us minerals in 2035. 8-year delay against permanent loss of knowledge about life's possibilities. Is 8 years really too long to wait?
November 2025, right now. The ISA is negotiating. The metals company is applying for US permits. Other companies are preparing applications. Best estimates? Commercial deep-sea mining begins between 2027 and 2029. We have maybe 3 years to change course. That's it. So what can we actually do? 32 countries have already called for a moratorium or precautionary pause on deep-sea mining. That's nearly 20% of ISA membership. France, Germany, Spain, the UK, Canada, these aren't small players. They're saying, not yet. Study first. In January 2025, the ISA elected a new Secretary General, Leticia Carvalho from Brazil. On the record, she stated that commercial mining should not begin until environmental regulations are complete and robust. That's significant. Leadership matters. Environmental groups are mobilizing. In 2024, WWF Norway sued their government for opening Seatinged areas to mining without proper environmental assessment. The lawsuit is ongoing. Major companies, Google, Samsung, BMW, Volvo, Volkswagen, have pledged not to use minerals from deep-sea mining. They're creating market pressure. And yes, individuals can affect this. Contact your representatives. The US is considering whether to approve the metals company's application. Public comment periods exist. Use them. Support organizations pushing for marine protected areas. Mission Blue, Deep Sea Conservation Coalition, Greenpeace. Spread awareness. This issue has been flying under the radar because it happens in places humans never see. Make it visible. Support ocean science. NASA's budget for astrobiology is $126 million annually. Ocean exploration? Roughly $30 million. We spend more on theme parks than understanding Earth's oceans. Here's the bigger picture. We're entering the era of ocean world exploration. Europa, Enceladus, possibly Titan, potentially dozens of exoplanets with subsurface oceans. These worlds represent our best chance of finding life beyond Earth in the next 50 years. Not Mars, not Venus. Ocean worlds. And Earth's deep ocean is our only training ground, our only reference library, our only chance to understand what life looks like when it evolves in darkness, under crushing pressure, in chemical environments that would kill us instantly. We can mine, but we can't unmine. Once destroyed, these ecosystems take longer to recover than human civilization has existed. So we're faced with a choice that feels absurd when you say it out loud. Would you trade the ability to recognize alien life for a smartphone battery that charges 20% faster? Because that's what we're actually weighing. The minerals will improve consumer tech and accelerate renewable energy by maybe a decade. The knowledge we'd lose might prevent us from ever confirming life on Europa. or recognizing it, or understanding what it means. Humanity has always been defined by our curiosity, by our drive to explore, to understand, to answer the fundamental question, are we alone? We've spent billions building telescopes to search for life around distant stars. We've spent decades studying Martian soil for traces of ancient microbes. We're sending spacecraft to icy moons, hoping to find biosignatures in subsurface oceans. And at the same time, we're preparing to destroy the only ocean world examples we can actually reach. The ISA meets again in 2026. Decisions will be made. Permits will be issued or denied. Mining will begin or be paused. You have a voice in this. Use it. April 2030. Europa Clipper arrives at Jupiter. Its 9 instruments will scan Europa's ice, measure its magnetic field, analyze plumes for organic molecules, map the thickness of the ocean beneath. Every biosignature it searches for was identified here, on Earth, in our deep ocean, at hydrothermal vents. What if it finds something ambiguous? Not clearly life, not clearly geology. And what if the vents that could help us interpret it are gone? Destroyed for minerals we needed in 2027. We don't know what will happen. Maybe we'll mine responsibly, study first, preserve critical areas, develop asteroid mining as an alternative. Maybe companies will bypass regulations, mine aggressively, destroy ecosystems faster than we can catalog them. Maybe Europa Clipper will find clear evidence of life, and we'll be grateful we preserved Earth's vents to help us understand it. Maybe it won't find anything at all, and the mining debate will have been unnecessary anxiety. We don't have the answer yet. And that's the point. The question isn't, will we find life on Europa? The question is, are we willing to preserve the knowledge that gives us the best chance? Science is patient. Science can wait a decade for minerals if it means keeping the library intact. The choice happens in 2026, maybe 2027. You're watching this in 2025. You have time to affect it. Those vents survived billions of years of planetary evolution. They witnessed the origin of life itself. They're teaching us how to recognize life in places we never thought to look. Don't let them disappear before we've finished learning. This is Cosmic Canvas, where we explore the universe's deepest questions, from the bottom of our ocean to the ice-covered moons of Jupiter. Learn more and take action. missionblue.org, deepseaconservation.org, isa.jm. Until next time, protect the library. The cosmos is waiting for us to read it.